Hello and welcome back to Electronic Packaging and Manufacturing course. If you recall, we were discussing thermal management and cooling strategies. Okay. So, in the last class, rather the last two lectures since we started discussions on thermal design and cooling, we have been talking about first we did a recap of the different modes of heat transfer, and then we talked about the important concepts of heat flux as well as thermal resistance. We had solved a very simple problem whereby we demonstrated the use of thermal resistance network in solving problems. Okay. So, today what we will do is, that was a simple exercise that we did. So, today what we will do is we are going to extend that and look at some of the very typical nomenclatures that are used while defining thermal resistance for electronic packages. So, that is going to be the concept covered for this lecture, thermal resistance for packages. Okay. So, let us move on to the next slide and let us see what we are talking about. So, this is a commonly used nomenclature. The thermal resistance is typically denoted by the symbol theta. Okay. The units, if we recall, is degree C per watt, and theta xy sub x in this as a subscript xy means it is the thermal resistance from point x to point y. Okay. And x and y can assume different values. Okay. So, x or y can be the temperature for ambient, or the point x and y can be ambient, can be board, can be case. We are going to look at what case is, junction, lead, thermal plate, heat sink. So, several of those. Okay. So, therefore, for example, if we are talking about the thermal resistance between the junction, which is a point within the piece of silicon microchip, and that is denoted by J for junction, and A is ambient, then the thermal resistance is going to be theta J A. Okay. Similarly, if there is a thermal resistance from the junction to what is called the case, and we will look at what case is, then we will call it theta J C, that is theta junction to case. All right. So, in a few slides we are going to see examples of these, what is and then what is junction, what is board, what is case, what is ambient will become, what is sink will become a little more clear. All right. So, this is theta and this is typical nomenclature. So, let us say somebody said what is theta JC. If you are a thermal designer, many people will ask for any new package that is designed, any package architecture, somebody say, Achha, what is the theta JC for this package? And you will say, oh, theta JC, I think that is typically around 1.1 degree C per watt. So, oh, is it so? Okay. What is case to ambient? And you would say maybe like 2 degree C per watt. Okay. So, something like that. All right. So, now the thing is, when we talk about thermal resistance and we are going to use thermal resistance network to solve problems, it is very important to understand where all the heat is going, how many paths does the heat have. So, it is generated at a certain point, in this case the microprocessor. From there, where does it go? And let us say, okay, from there it finally goes to the atmosphere, goes to the ambient, that is where it is dissipated. Okay, fine. But while going there, what are the paths it can take? Does it have only one path to go, or can it have multiple paths? Okay. For example, in the small problem that we solved in the last lecture, we considered only one single heat flow path from the junction to the thermal interface material to the copper plate and then to the ambient. Okay. Now, there could have been a parallel path from the junction to the package to the substrate to the motherboard, then to the ambient. Okay. So, these are then two parallel paths, and then there can be multiple ones. We will see some of those. So, what I am trying to say is, it is very important to understand the heat transfer paths, what are the different routes the heat, the thermal energy can take while flowing from point A to point B. Okay. Now, unlike electrical current that travels only through electrical conductive paths, heat goes everywhere. Okay. Now, probably the electrical engineers is not probably will say this is technically not correct, because even if it is an electrical insulator, there will still be some teeny mini movement of electrons and all. But for heat, as long as there is a medium, there will be heat transfer either by conduction or convection. And even if there is no medium, there can be heat transfer through radiation. Okay. So, heat goes everywhere. You cannot say, because there is no perfect insulator. You can have a material with very, very low thermal conductivity, a solid material, but still there will be some amount of heat. Okay. And then we have to take a judgment as to whether we want to neglect it or we still want to consider it. So, the key to good thermal design and experimentation is to understand how and where heat flows and to quantify it. So, which is again trying to identify through what all paths can the heat flow from its point of generation to the final point of dissipation. Okay. So, if that is the case, then let us move on to the next slide, and we will look at one of a simple package. As you can see, this is a pin grid array. Okay. It is a pin grid array. It's a very old Intel package. It's a schematic of that, and what you see is you cannot see the piece of silicon inside, because it is covered with a copper heat spreader. Heat spreader is like a plate. Okay, and we will see a schematic in the cross sectional schematic in the next direction in the next slide. Okay. So, this is the substrate or the chip carrier onto which the chip is bonded, typically flip chip bonded, and with a copper spreader on top. Okay. And then this substrate has pins. So, the attachment to from the substrate to the motherboard is through a pin grid array. All right. So, if we look at this plastic pin grid array package, what will I have? If I look at the cross section now, what I have is the following. What we saw before was this piece of silicon, which is denoted by gray, and then a piece of copper on the top, and then what has come out as orange is really this substrate. Okay. Now, between the silicon and the substrate, there will be the solder balls, so on and so forth, which I have not shown. Okay. So, there is a piece of silicon resting on a substrate, and then there is a copper plate on top, and the substrate then with the pins goes to the socket, which is denoted by this light blue, and which in turn is attached to the motherboard denoted by green, or the circuit board denoted by green. Okay. So, socket, PCB, the pin grid array package, the piece of silicon which is the microchip, and the copper spreader, and then on top of that typically we place what is called a heat sink, and we are going to see some of these in probably the next lecture. Okay. So, heat sink, we will see that, but that is at this point just consider it to be a medium which helps in effective heat dissipation. Efficient heat dissipation, increases the heat transfer rate. All right. So, if this is how it looks like, then what are the different paths in which the heat that is generated in this piece of silicon can flow? And you can see that this is extremely complicated. Okay. It can flow by conduction from this piece of silicon to the copper, and then to the heat sink, and finally from the heat sink to the ambient. Okay. So, conduction is denoted by pink, and from heat sink to the ambient will be by convection, which is denoted by blue. But again remember that radiation also occurs. Okay. It can be a small component, you can neglect it, but radiation, if any surface is at a temperature above absolute 0, then it is going to emit radiation. Okay, and then there will be a net radiation heat transfer from that surface to the ambient. Okay. So, that is what is going, that is one path. So, through conduction from the silicon to the heat spreader, then to the heat sink, and then by convection to the ambient. What else? It can also take a path in the downward direction. So, there will be some heat that will flow from the silicon to the substrate, and then through the pins into the socket, and then again from the socket to the motherboard, all by conduction. So, hence denoted by pink, and then from the motherboard to the ambient by convection and a bit of radiation. Okay. That is another path. Then you can also say, okay, whatever comes to this from the silicon to the substrate, part of it will be conducted, but part of it will also go to the side surfaces, and from where it is going to be lost to the ambient by convection and radiation. Same for the socket. So, you can see it is a very complicated heat transfer path, many parallel paths in which the heat can flow. Okay. And we have to quantify each of these, and in order to do that, I need to have a means to quantify the thermal resistance offered by each segment in the heat transfer path. Okay. So, this is the case here. So, if I draw a thermal resistance network, this is how it is going to look like. Extremely complicated, as you can see, right. So, something that I am not talking about right now, you can see these resistance from this point to this point, even though both are in the motherboard. Okay. There is a resistance from here to here. Okay. These are something called a spreading resistance. Okay. Whenever spreading or constriction resistance, whenever heat flows from a smaller area to a larger area, okay, apart from just the L over K A, which is the pure conduction resistance, 1D conduction resistance, there is also additional resistance due to spreading. Okay. We will talk about all these when we solve problems. Okay. All right. So, this is what it is, and so as you can see that if I have to draw a thermal resistance network for a package like this with a heat sink on top, as shown here, the thermal resistance network can be very, very complicated. You see lots of resistances, some in series, some in parallel, so on and so forth, and you have to come up with an equivalent resistance, right, using the series and parallel rules, which will help you find the temperatures at some of these intermediate points, as well as the total heat flow in each of these directions. It is very common that, it is very likely, I would say, that if you do this whole analysis, you will see that the thermal resistance in this downward direction is very, very large compared to the upward direction into the heat sink, and that is the whole idea. Okay. So, as a result, most of the heat, maybe more than 90%, 90 to 95% goes in the top direction as shown in this picture, and a lot less comes down in the bottom. But that may not be the case. If this heat sink was not there, then we do not know what will be the split. It may be 60-40 instead of 90-10. Again, whether this heat transfer from the heat sink to the ambient, whether it is by forced convection or natural convection, will also depend the split, because forced convection, the thermal resistance is going to be much lower compared to natural convection. Okay. So, all these play a lot of importance. Okay. And therefore, what did we start by saying? That it is very important to identify the heat flow paths, and only then can we come up with an accurate thermal resistance network, which is going to help us quantify the heat flow in different directions. Okay. So, now let us look into what is called thermal architecture. So, there are two very common thermal architectures for a silicon in the computing world. So, one is called the bare die attach and one is called the integrated heat spreader. Okay. So, the first one I am going to talk about is bare die attach. So, here the silicon is this green portion, is this one. Okay. As you can see, it is flip chip bonded onto this substrate, correct. So, these red elongated spheres, as you can see, elongated circles as you can see, are the solder balls. It is a cross section, and then what is around the solder ball is that underfill epoxy, if you recall. Okay. The silicon is bonded onto the substrate, flip chip bonded, and this is the underfill epoxy. Okay. The substrate in turn will have ball grid array, and it will be attached to the motherboard using this ball grid array. Okay. So, it is ball grid array from flip chip bonded with BGA from the silicon to the substrate, and again from the substrate to the motherboard, which is not shown here. Okay. Now, what happens is, why is it called bare die attach? Because the heat sink is directly attached onto the silicon. The heat sink, as you can see, which has base and what these are called fins, we will see this in the next lecture. So, this finned heat sink is directly placed on the silicon, and in this case more correctly on the back side of the silicon, because this is flip chip bonded. Okay. And the issue is that, again, as we were talking about yesterday in the last lecture, sorry, that no two surfaces can be perfectly bonded, because these are solid surfaces, there is nothing called absolutely flat surface. So, therefore, in order to fill in the voids, we need a thermal interface material, and that is what is shown over here. Okay. So, the heat sink is placed on the piece of silicon with a layer of thermal interface material in between. Okay. So, this is useful in mobile applications. Mobile, as in when I say mobile applications, it is not strictly mobile phones, it also means laptop computers, and I would say primarily laptop computers. Actually, this is not absolutely true, we will see that later. In a laptop, there is typically not a heat sink that goes right on the silicon, there is something else called heat pipe, we will talk about that later. But bare die attach means that there is a heat sink or whatever is the cooling solution directly bonded onto the silicon with, of course, a layer of thermal interface material in between. Okay. The other one is the integrated heat spreader architecture 2, where what happens is, above the silicon you have what is called a heat spreader. It is typically a copper plate, or sometimes also you can also call it, many people call it the lid, LID, lid. Okay. So, it is in the form of a copper plate which is bent at the edges in the form of an U, and inside this is the piece of silicon, and again between the copper and the silicon you have a layer of interface material. Okay. And then the heat sink is placed on this integrated heat spreader. Okay. And again we have a second layer of interface material which is shown by these hashed red lines over here. Okay. So, what is the difference? Over here there is only one layer of interface material, and many a times we call it TIM 1. Over here there are two layers of interface material, one between the silicon and the heat spreader, which is called TIM 1, and then between the heat spreader and the heat sink, which is called TIM 2. So, two interfaces, therefore, two layers of interface materials. Okay. What I also want to say at this point is, again thinking about the industry and the way it works. So, we have this semiconductor chip manufacturing companies, Intel, AMD, okay. And then we have these companies who actually sell the final product, the final computer, which we call the OEM, and these include Dell, HP, Apple, and so on and so forth. Okay. Toshiba, Sony, Fujitsu, all these companies. So, what happens is Intel or AMD, the microprocessor company, in case of architecture 1 sells this part, sells the silicon, sells up to here the silicon bonded onto the substrate. But in case of architecture 2, it sells the silicon on the substrate and with the heat spreader attached onto it. Okay. And the remaining thermal solution, what kind of heat sink, what kind of thermal interface material in the second layer, etc., or in this case the first layer, that will be determined by the OEM, the Dells and HPs of the world. Okay. Intel or AMD can provide a guidance, but final decision as to what goes into the product lies with the computer equipment manufacturer, okay, not the microprocessor manufacturer. So, that is also important to know. Apart from architectures, who controls what and who designs what is something that we should know. Okay. So, now if we look at both of these architectures, architecture 1, architecture 2, and at this point what we are saying is we will neglect the heat transfer to the bottom. We will assume that majority of the heat flows in the direction of the heat sink, and what flows in the other direction towards the board, towards the socket, from the substrate to the motherboard is negligible. If that is the case, then these are the heat flow paths. From the silicon it is generated, okay, this is where the ball grid array, that is where it is going to be generated, and then it goes up and then by convection and radiation from the heat sink to the ambient. Except that in this case, in the conduction path, you will have the silicon and TIM 1. Over here you will have silicon, TIM 1, heat spreader, TIM 2, then heat sink. Clear? So, if I do the bare die attach, these are the 3 temperatures that we talk about. Okay. Tj we have already discussed, T junction, okay, that is inside this piece of silicon, that is the hottest temperature, that is because that is where the heat is getting generated. So, Tj, typically if somebody is, for example, Intel or AMD is selling this microprocessor, they will say Tj cannot exceed 100 degrees centigrade or Tj cannot exceed 80 degrees centigrade. So, these are all specified, Tj max, that limit is set, and so the thermal solution designer now has to come up with a thermal solution such that to ensure that the Tj does not exceed that maximum allowable limit. Okay. So, Tj very important temperature value. What next? Ts, what is the temperature at the heat sink base, that is Ts, and then finally Ta, which is T ambient. All right. So, assuming these 3 points, the junction, the sink and the ambient, we can define a resistance from junction to sink, so theta Js, a thermal resistance from sink to ambient, which is theta Sa, and since these are all in series, we can say that theta Js plus theta Sa is theta Ja. Okay. So, now therefore, think about it, if you can quantify theta Ja, what is the junction to ambient resistance? Let us say I say it is 3 degrees C per watt. Okay. And then I tell you that my ambient condition is 30 degrees and my theta j, my Tj cannot exceed 90 degrees C, Tj max is 90 degrees C in an ambient of 30. Then what is the maximum Tj minus Ta I can have? That is 60 degrees, 90 minus 30. So, then what is the maximum amount of heat that can be dissipated in this path? That is going to be 60 degrees, which is Tj minus Ta divided by theta Ja. So, 60 degrees divided by 3 degrees C per watt, so or 20 watts. All right. So, what I am trying to say is, let us say you are given a problem and where you are told that Tj must be less than equal to 90 degrees C, T ambient is 30 degrees C and theta Ja is 3 degree C per watt. What is Q therefore? Q is therefore Tj minus Ta divided by theta Ja, and that comes to 20 watts. So, therefore, the thermal designer is going to put the ball back in the court of the electrical designer and say, you know what, if this is what you are talking about, I have done these calculations, and if this is the limits, these are the limits that you are going to set, that in namely that Tj cannot exceed 90 degrees in a 30 degree ambient, then I am unable to cool with the current solution. The maximum power that I can dissipate, so maximum cooling that I can provide is 20 watts. Is that enough? So, the TDP, the thermal design power, is 20 watts. So, whatever architecture you do in this piece of silicon, make sure that the power dissipation under any workload does not exceed 20 watts. Otherwise, this thermal solution is not going to work. Okay? Or you have to relax this Tj limit and make it, let us say, 100 degrees, 105 degrees. Okay? So, this is how the correspondence between the electrical and thermal engineers go. Clear? Bare die attach. So, package with IHS example, similar thing, except now here we have another additional temperature. We also have what is called the case temperature Tc. Remember, I said that I am going to define what C is, the case is. This is what the case temperature is. It is the temperature on the surface of the heat spreader, Tc. Okay? So, this heat spreader comes with different names. Integrated heat spreader is the most technically correct name, but people use words like lid, people use words like case. All right. So, and these are not unjustified names, because apart from what is called spreading the heat and giving it more surface area for dissipation, what it does is the heat spreader also protects the silicon inside from external factors, right. So, that way it is also a case or a lid, right. Okay. So, in this case what happens? The 4 temperatures: junction, case, sink and ambient. By the way, practically it is very difficult to measure both the case and the sink, because they are very close to each other, and what separates them is a layer of interface material. Okay. So, in this case, however, if I have to draw the theta resistance, or if I have to write down the thermal resistances, I will have a theta Jc, I will have a theta Cs, I will have a theta Sa, and the sum total of them is going to be theta junction to ambient. Okay. So, again here also, if I am able to calculate these resistances, then I can, given the temperature constraints, I can define what is going to be the maximum power that can be dissipated, and therefore, what is going to be the TDP that this package is able to withstand. Okay. All right. So, sometimes theta can be calculated, sometimes theta is measured. Okay. You know how much power you are putting in, and then you measure the temperatures and determine what is theta. Okay. The advantage is thermal resistance is independent of environment. It does not depend on the temperature. Not fully correct, I would say, but except especially for radiation and even for natural convection. Okay. Because thermal resistance, especially if it is H, the H for natural convection does depend on the temperature difference between the hot and the surface and the cold ambient. All right. But more or less it is in a given range, it is more or less can be assumed to be independent or very weak dependence on the other factors. Okay. Indication for better package designs and materials, because if you can measure it, you can say, oh, this theta is very low, which means this is a good the thermal solution is very good. Okay. And it is very good, as we saw, that this is a very useful tool to make quick estimations, system level thermal simulations. If you want to go for system level thermal simulation, okay, we will see that later. I am doing a modeling of the entire motherboard with all these components. Are we going to model each of these, every layer of the interface material, every heat sink? No. We would just put this package at the place, and define a thermal resistance in both directions, towards to the ambient, to the board. Okay. Now, what are the disadvantages? It is very difficult to measure these thermal resistances separately, because sometimes these temperatures can be so close. Also, where do you put the thermocouple? So, the measurement is not easy, and it is very sensitive to measurement error. Think about, if I want to measure the temp in the previous slide, if I want to measure the temperature of the sink Ts and Tc, it is impossible. Okay. Where do you put the thermocouples are going to collide with each other? Okay. So, there are certain disadvantages, but all said and done, theta is widely, theta Jc, theta Ca, theta Ja, theta Js, these are widely used parameters in the electronics packaging industry. Okay. People use it, engineers, practicing engineers use it day in and day out. And when I say practicing engineers, these are not the of course, the thermal engineers do come up with these values. So, they have to think a lot more. They have to worry about conduction, convection, radiation, how can I do this, how can I increase heat transfer coefficient, all that stuff. That is their job. But their final aim is to reduce theta as much as possible, and then give this value to the non-thermal engineers, who are then going to use this value for their package level models, system level models, to determine what is the maximum power that they can put into this piece of silicon, so on and so forth. Okay. From that point of view, this is very, very useful. Okay. So, thank you very much. That is all I wanted to cover for this lecture. Just to recap, we covered the concept in the last class. We talked about what is thermal resistance, and we did a small exercise problem. Today, we went deeper into actual package architectures and looked at what are the different thermal resistances, what is the different heat flow path, and how complicated a thermal resistant network can become, and so on. Okay. So, while discussing all these, we talked about a cooling solution called a heat sink. What is a heat sink? We are going to take it up in the next lecture. Thank you very much.